Let's take a step back now and think about what we've just discovered about alternating series. We can start with a series that diverges to infinity, like the harmonic series, for example, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, etc., which we've shown diverges. It heads off to infinity. It grows without bound forever and ever. But then if we take the every other term and we change its sign so that it becomes an alternating series, like the series shown here, the alternating harmonic series, then that's enough to make it converge to a very small value, or at least a finite value. In this case, we talked about how this alternating harmonic series converges to something around 0.69, which is a far cry from infinity for sure. So when we have a series that does that, a series that would diverge if it were all positive terms, but ends up converging when you turn it into an alternating series, we call that a conditionally convergent series. So that would be one of these deals right here. Conditionally convergent, meaning that the absolute value of the series diverges, but the alternating series converges. Okay. The other possibility is that the absolute value of the series converges along with the alternating one. So if that happens, then we say that the alternating series converges absolutely. Think about the absolute value. It converges absolutely. All right, so let's not make this too overly obtuse. I'm going to change this so that it's not quite so crazy. We're going to check for the convergence of just a regular alternating series. No need to make things more confusing than they already are. So we're going to make this just a regular alternating series. And the first question I would ask here, we could jump right into the AST, the alternating series test, and say, well, does it pass the first check? Does it pass the second check? If so, then it converges. But here's a better deal. First, consider the absolute value of the series. In other words, consider the sum from n equals 1 to infinity of not the alternating series, just 1 over 3 to the n. Now, this we should recognize as a geometric series. And we know that this converges by the geometric series tests because the absolute value of r is equal to 1/3, which is less than 1. So I want you to think about this. We start off by adding a whole bunch of positive values, and we get something that converges to a finite value. Then we take that same list of values and make half of them negative. Leave the other half positive and make half of them negative. We're subtracting half of the terms instead of adding them. So, of course, this is going to converge as well. So we don't have to do the alternating series test for this one. We can just say, because the absolute value of the series converges by some other tests, we can then conclude, therefore, the original series converges absolutely. Again, because the absolute value, because the absolute value of the series already converges. So we don't have to go through the steps, all right? So if we try this one, we might recognize this one. We can kind of do these in our head, right? We can think about this and we can say, well, I know that we're going to consider the absolute value of the series. That would be the first step. And in our heads, we can kind of see that this is going to be 1 over n raised to the 2/3, right? That diverges by p series because p is equal to 2/3, which is less than or equal to 1, right? So that is the only time that we have to absolutely go into the alternating series test. So we have to do the two parts of the alternating series test because we don't know whether this thing converges or diverges. We just know that the absolute value diverges. So now we're going to go into the other part, the part that we talked about at the beginning of this section, and ask the question, does the limit as n approach infinity of 1 over n to the 2/3 equal 0? And the answer is, of course, yes. The second question is it true that the n plus first term, so n plus 1 raised to the 2/3, is it true that that is always less than or possibly equal to the nth term? Okay, and we can pretty quickly verify that. We can multiply both sides by n to the 2/3. We can multiply both sides by n plus 1 to the 2/3. We can raise both sides to the 3/2 and get n is less than or equal to n plus 1. And I'm pretty convinced that that's a true statement. So sure, therefore, the original series, which is negative 1 to the n over the cube root of n squared, converges for sure. It converges by the absolute series, or the alternating series test, converges. But because the absolute value of the series diverges, we specify the type of convergence. This converges conditionally. The condition required to allow this to converge is that it has to alternate. So it converges conditionally by the alternating series tests. Okay, so you should always check the absolute value of the series first, because if it converges, then we save ourselves the time of doing all of this stuff. If you can, in your head, realize that, no, I shouldn't say that. You should still show this so that we can verify that, that the series converges conditionally versus absolutely. All right, fun fact. Take a conditionally convergent alternating series and reorganize the terms. It is possible to change the value to which the series converges. Anyway, I'll leave you to chew on that.